Alright, hey guys, what's going on? So today we are going to be talking about getting the Proca Lagrangian from, or the free theory again from the 1/2 representation. So we've talked about the 0, 0 representation, we've talked about the 1/2 0, 0, 1/2 representation, now we're talking about the 1/2 representation. There's a lot, we've gone over a lot so far, and we're not even brushing the surface of this content yet. We're going to get into gluons and leptons and quarks and all this kind of stuff, and getting into really the mathematical details of what these things are in this playlist. And then from there, I'm thinking about potentially building the standard model from all of this. It's going to be super interesting. It's going to be super fun. But anyways, if you like this kind of content, make sure to hit that like and subscribe button, and let's get into it now. All right, so we are talking about the Proca Lagrangian. We're going to derive the Proca Lagrangian from, again, group theory. That's what we've been doing for the past 3 videos. We derived the Klein-Gordon from group theory. We've derived the Dirac equation from group theory. Now let's do the Proca equation from group theory. So the way we're going to start this is the way we started the last 2 videos, is we're going to define the invariants. In the first video on scalars, we defined what exactly were the scalars, what exactly were terms that gave scalars. Scalars are always invariant. Then we went on to the Dirac case, and we said, okay, what are the invariant terms there? We needed the charge conjugated spinors to do that. And now we are talking about the invariants, the invariant property, or the invariant objects, mathematical objects within this representation. And these are the invariant objects, right? These are actually not too difficult to see how they're invariant, right? Because they're all just dot products of vectors, right? You take this guy as a vector, this guy's a vector, right? That a dot product of a vector is, again, that's a scalar essentially, and that's invariant. Here again, dot product, 2 dot products again. Okay, this again, 2 dot products. This guy here is a little bit weird. Let's take a look at this guy, because suppose we had a constant in front of this guy here. So our Lagrangian plus this term, we apply the Euler-Lagrange equations, and when we do that, we get, okay, well, the derivative here is just going to be, the derivative of this with respect to a mu is just going to be 0, right? The derivative of this with respect to that is, well, that's just going to be c, right? Because this here matches this here, so that's just going to be c. And so what we get is, again, a constant, and we recovered this, just the first part of this Lagrangian, or the Euler-Lagrange equation, right? Because this guy went to 0. There is no a mu terms in this. There's just derivatives of a mu terms. So I4, therefore, doesn't really influence the equations of motion. You can sort of, this logic again went back to the logic behind developing the Klein-Gordon equation, where if you just get a constant out of the Euler-Lagrange equations for these invariant objects, you can effectively just ignore that one. It doesn't contribute to the equations of motion. It just shifts the equations of motion. But anyways, so now our Lagrangian looks like this. So in our 1/2 representation, it looks like this, right? So we have a weighted sum of each of the invariant objects. Using the right-hand side of the Euler-Lagrange equations, right? So this is our right-hand side of the Euler-Lagrange equation. We get all of this, right? So how does this come about? Let's piece this apart. All right, so C1, that's just a constant. So d mu, so derivative of d mu a mu, that's this right here. And then the d underscore mu, d a nu, well, that's right here. And then we have this derivative here. Again, where this is really just product rule, right? And so this here is really just a product rule. Okay, let's see what we can do now. Well, the derivative of this with respect to this is only going to be something if mu equals, well, I take that back actually. So that I'm skipping this step, right? I don't want to skip this step yet. What we're doing is we are going to actually raise and lower indices, right? So, because this guy's a lower index, these guys are upper indices. So let's lower these indices, right? So to lower these indices, we have k and lambda. So in order to retain this form here, we need these two metrics. And if you're not aware of how this works, again, the metric tensors, again, you can do the Minkowski metric also, but the metrics are the things that raise and lower indices. This is sort of a tensor calculus mathematical thing. I have talked about this a little bit in my very early general relativity course about raising and lower indices. For right now, I don't want to really get into the details about why the metric raises and lowers indices, but for right now we're just going to say it does. Okay. So these metrics are going to raise and lower indices, because you can see here the k and the k in the lower, k in the upper, lambda in the lower, lambda in the upper, and what we're left with is mu, nu, and upper, mu and nu and upper. All right. I'll undo all those marks just to make things a little bit clearer. But so that's this term. Oh, that's this term right here, and we don't change this term. And we'll see why we don't change this term. Okay, so now that we have everything, these two guys are lower indices, these two guys are in lower indices. Now we could say, well, the derivative of this with respect to this is only going to be something if k is equal to mu, or k is equal to sigma, and lambda is equal to rho. Okay, so we can actually replace this. This is only a thing, right? This is only a thing if it's going to be 1, right? If they're equal. If they're different, then it's going to be 0, right? So that's where these two guys come from. These are delta functions. There are 0 everywhere except for when the indices are equal to each other. All right. So what does that do? Right. So that will actually. So what this actually does, right? So let's see here. So d sigma a rho. Right, so here's the sigma and the rho. So that's actually, well, I'll zoom in here. So mu, nu, nu. K, sigma, or not sigma, lambda. So it's left in upstairs. It's going to be sigma and rho. Okay. Same thing here. Mu, nu. So sigma and rho. Okay. And so what this leaves us with is d sigma a rho, d sigma a rho. Okay, right there. And then we get this, right? So these two guys are the same thing. So we bring a 2 out here. All right. Similarly, now this whole process right here can be done for this term. So we just looked at this term, but we need to do the same thing for this term. And what we find out, just to save ourselves a little bit of time, is that all of this for the C2 term is equal to this. So putting both of them together, we have these two guys. And then our last term is here, right? And so the derivative here is just going to be 2, right? Because we can think of this as a mu squared with some sign differences, but again, that squared is going to be, a 2 is going to be right here, and that's where, so our C3 term is going to be there. Okay. So that's, so that is all of, that's all of this, right? So we took, this guy right here is a product of our Euler-Lagrange equation, right? And so again, what we did here is we said, so these are all the terms that had the derivatives in them. This was a part of the Euler-Lagrange equation that dealt with those. Then the other part, the right-hand side of the Euler-Lagrange equation, took part in this, or the left-hand side, right? So the other side of the Euler-Lagrange equations took care of this term. That's what that other side is, right? If you recall, the other side of the Euler-Lagrange equations was that. Okay. All right, so we have this. We can divide both sides by 2. And then setting C and, so again, these guys are constants, right? These two guys are constants. So we set them to 1/2. We set C3 to m squared. Well, okay, that's the Proca Lagrangian. All right, so this, again, that's just the Proca Lagrangian, right? And the reason for that is we didn't plug, so we have 1/2 here. But so when we set these two guys, these constants, we really just put the constants back into here, right? And that is where we get this. All right. Okay, so we can actually unclutter a few things, right? Because this is kind of long, it's kind of bulky. We can unclutter this a few things by defining our electromagnetic field tensor. And the way we define it is this way, right? So F sigma rho is equal to D sigma A rho minus D rho A sigma. And in this way, then we can say we have upper indices, lower indices, lower indices. This term here then equals all of this when we multiply everything out. Since these are all dummy indices because they're on both sides of the equation, we can swap dummy indices as I'm doing here. And then we can recognize that, okay, here's d mu a nu, here's d mu a nu, here's d nu a mu, and d nu a mu. So these, what's in green are the same, what's in blue are the same. So the d mu a nu parts here, and the d nu a mu parts right there. And we have 2 of each, right? 2 of each, so there's the 2. 2 divided by 4 is, or not, yeah, so this is not 2 divided by 4, right? This is going to be 2, and that's going to go into turn into a 2. And, oh, there we go. Like that. So that's where we get the 1/2 from, and we have all this, right? Well, what's all this? This is the first part of our Lagrangian, right? That was this part right here. All right. So this is our Lagrangian in our 1/2 representation. What we have done, ladies and gentlemen, is we've got the Lagrangian for our scalar field. We've got the Lagrangian for our Dirac field. And we now have the Lagrangian for our Proca field. Another way of saying these is we have a representation of, we have different representations, or different Lagrangian representations, if you will. All of them are invariant under Lorentz transformations. Okay? Because they're all built out of invariant terms within each representation. So the way, an interesting way of thinking about this, again, is we have Lorentz transformations. All right. We have this world of Lorentz transformations. Here's our world of Lorentz transformations. And we have a Lagrangian, right? So we have a 0, 0 Lagrangian. We have a 1/2 0 Lagrangian and a 0, 0 1/2 like this, and then we have a 1/2 1/2 representation. An interesting thing here is we could ask the question, are these Lagrangians really one and the same thing? Well, the answer to that is yes, right? Because if you go into my quantum field theory playlist, what we found out is that you can actually show that these two guys are all really just variances or different representations of an oscillating Lagrangian, not an oscillating, of the scalar Klein-Gordon Lagrangian. It's just that they're different representations, right? That there, one is in the spinor form, or is in the spinor representation, and the other one is in a vector representation. But they're all sort of the representations of a grander scalar representation, which sort of begs the question, right? Is there really only one Lagrangian for the universe? It's kind of interesting to think about. And what we want to do here is, so what we're going to do is we're really going to focus on these three representations. We're going to get a lot of interesting physics out of them. And from that, then we're going to ask this question again. And then after we ask that question, we're going to dive into building the standard model. So with that being said, I hope this sort of leaves you thinking about exactly what Lagrangians are and how Lagrangians can be represented in different ways. And the three different representations, again, are the scalar, spinor, and vector representations. With all of that being said, this is what we got for free theories, right? The next upcoming video is going to be probably a long video on interactions or interaction theory. And this is really where things are going to get wild, right? Because the idea here, the idea going forward, is that each and every one of these fields needs to interact with a specific type of spin 1 field. All right, spin 1, again, being, these are spin 1, these are spin 1/2, spin 0. The idea here is that there needs to be interactions between spin 1 fields in order to be invariant under local transformations. And we're going to define what a local transformation is in the next video. But again, the whole point is that we want Lagrangians to be invariant, just like we want the metric to be invariant. We want Lagrangians to be invariant. And in making them invariant, we need to consider all types of transformations. We need to consider global transformations. Those are transformations that don't depend on where you are in space. But then there's transformations that do depend on where you are in space. And we need to make these Lagrangians invariant under both conditions. Right? Because, again, the name of the game is to render them invariant all the time. And because that's where we're going to get the interesting physics. Okay? So when we render them invariant, when we get into interaction theory, what they need to interact with are spin 1 fields. That's going to be the big point that we want to make for these, probably the next 10 or so videos. We want to keep this in the back of our mind because this is where the idea of gluons and leptons and quarks are going to really shine, is when we have this idea that there needs to be these gauge interactions, right? The gauge interactions, those are the gauge fields or the spin 1 fields. Okay. We're gonna repeat this throughout the entire playlist, just to make sure it's drilled into our heads. But yeah, if this is the kind of content you really like and you're interested in, make sure to hit that like and subscribe button. Go onto my Patreon page where you can get early access and soon to be exclusive content. And yeah, with that being said, I will see you guys in the next video.